chapter Mechanic of Materials, chapter 14, Energy Method, Strain Energy in Beams. This question is a very interesting question and is a sample of P and S equation. So if we have two identical beam handling both handling concentrated load at their center, one has two simple support and the other has two fixed support. If both of there has the length of L, we want to know what is the ratio of strain energy of the first beam to the second one. We'll solve this problem with different approaches. So just let's get it started. The first solution is a classical method which includes a integration method and it's a longer solution. So if we just cut the, for example, beam 1 by the length of x and create the moment equation, we do know due to symmetry, we do have a RA is P over 2 and RB are P over 2. So summation of moment about x goes 0, it just gives us mx minus a half of p times x goes 0, and that says mx1 is equal to a half of p times x. If we do the same for beam 2, and at the same time we do know a concentrated load applied to a both fixed end develops a moment of PL over 8. So MA is equal to MB, that's the fixed moment, PL over 8. And if we develop the moment again about point X, so summation of moment about X including the fixed end moment at A goes 0, it just gives us mx plus a 1/8 of PL minus a half of P times X goes 0. And it just gives us the second equation, moment of X for beam 2, that's P over 2 times parenthesis X minus L over 4 times close parenthesis. So we do know a strain energy. We do know a strain energy is 2 times integration of 0 to half of halfway through m squared strain energy due to bending moment in beams, which is the common case. That's m squared over 2ei times dx. And if you do the math, it just gives you 2 times, let's take the constant out of the integration, then integration of 0 to L over 2 x squared dx. And if you do the math, it gives you u1 p squared L cubed over 4 times 3 times 8 ei. And if you calculate the strain energy for a second beam, that's again 2y because halfway through to integration of L length 0 to L over 2, again m2 squared this time over 2ei dx. And let's take the constant out of integration, that's a p squared over 4ei, and then integration from 0 to L over 2 x minus L over 4 in parentheses squared dx this time. So if we expand this in this integration and then simplify that, it just gives us this equation from 0 to L over 2. If we simplify the equation, it just gives us 1 over 3 times 4 times 8. And if we just rearrange that based on u2, it's just p squared L cubed over 4 ei from the previous part times 3 times 4 times 8 from the integrational part. And if you divide u1 by u2, it just gives you the parametric value of u1 at numerator and parametric value of u2 at denominator. And if you simplify them with each other, all the parameters cancel out and you will left with a number 4. This was the classical method and involving the integration and developing the moment equation based on length of x. And now let's solve the problem in a far simpler approach. So the quick method if is the area under P delta. Strain energy is the area under force displacement area. So the area of uh, under force and displacement, that's a half of, that's the area of this triangle, is a half of P times delta, and that's equal to strain energy due to energy method section. Mhm. And if you just resemble or mimic a beam with a spring, that's a, if you pull or push a spring, a delta is force is equal to P is equal to K times delta, and K is the spring stiffness. So in that case, delta is equal to force over K. Mhm. If you replace this in the equation of strain energy, it just gives you a strain energy is equal to force squared P squared over 2 stiffness of spring or beam. Hmm? Now, by knowing this fact and simulating beams like a spring, for this case, delta max is equal to P times L cubed over 48 EI. And that's the calculation of chapter 14, chapter 12 of mechanics of material in beam deflections. And that gives us a K1 or stiffness of this spring or beam is equal to 48 EI over L cubed. So, and if you do the same process for second beam, it just gives you a delta maximum of 192 EI over L cubed. You can do the calculation for delta maximum in moment area or a integration method or any other method you know, and then K2 is equal, and if you want you can review chapter 12 which is related to beam deflection. It just gives you K2 is equal to 192 EI over L cubed. So that's a stiffness of beam 1, and that's the stiffness of bending stiffness of beam 2. So U1 over U2 due to formula is P1 squared over 2K1 over P2 squared over 2K2. Because both of forces are equal, so P1 and P2 cancel out, and these two is cancel out together, and we just remain with the K2 over K1, which is 192 over 48, which again gives you a numeric value of 4. Thank you. We'll solve more interesting problem like this in next videos. Thank you.